Radicals, radicals everywhere. In equations where radicals appear on both sides of the equation, we're still able to apply the power rule of radicals. Raising a term in a radical to the power of the index cancels the radical. If both sides have radicals to the same index, both sets of radicals are canceled. It's a little more interesting when they're not the same. That's kind of like finding the greatest common factor and raising it to that power. But don't worry, we're going to only be solving where they are the same. And here's our first one. So this is in your notes. So we're going to solve, I think all of them are in your notes. We're going to solve the radical equation and check our solutions. All right, so on both sides we have cube roots. All right, so we're going to cube both sides. So we have the cube root of 6x plus 9 cubed equals the cube root of 10x minus 3 cubed. All right, so cube and cube root cancel on both sides. We have 6x plus 9 equals 10x minus 3. And now we're just going to solve for x. So we'll subtract 6x from both sides. So we have 9 equals 4x minus 3. And then add 3 to both sides. 12 equals 4x. And then divide by 4. So 3 is x. That's our solution. Now let's see if it's in a good solution or an extraneous solution. All right, so we're going to plug into the original equation and check. So we have the cube root of 6 times 3 plus 9 equals the cube root of 10 times 3 minus 3. Right, so the cube root of, so it'd be 18 plus 9, so that's going to be 28 equals, oops, wait. Whoop. 18 plus 9, which is 27, equals the cube root of 30 minus 3, which is 27. The cube root of 27 is 3. Both times. That checks out. This is a good solution. It gets a happy face. There we go. All right, that solution worked. So all of these, on all of these problems, we're going to have radicals on both sides. So you really can't do a lot of isolating like this one. Notice there's a coefficient. It really is kind of pointless to divide both sides by 2 because you just end up with a 1/2 on the other side. All right, so instead we can square that. It's not that bad because it's a product. So we have the square root of 5x plus 9 squared. We have to square both sides to eliminate the radical. And we're going to square the 2 as well here. We're going to square 3x, the square root of 3x plus 4 squared. So the coefficient will be squared too. All right, so that's just the, we're just raising the 2 to a power. And we can do that when we have a product, not a sum or difference. Square and square root cancel, so we have 5x plus 9. All right, so this is going to be 2 squared times 3x plus 4. Make sure you use parentheses here so you remember to distribute, right, that 4, which is what it's going to be as soon as we multiply it or raise to the power. So we have 5x plus 9 equals 4 times 3x plus 4. We'll distribute the 4. 5x plus 9 equals 12x plus 16. We'll subtract 5x from both sides. So we have 9 equals 7x plus 16. Right, and then we'll subtract 16 from both sides. Right, so that gives us negative 7 equals 7x. And then divide by 7. And I'm running out of space. I should have wrote it a little smaller, I guess. Negative 1 equals x. Right, so now we got to check our solution and make sure it's good. All right, so we have the square root of 5 times negative 1 plus 9 equals 2 times the square root of 3 times negative 1 plus 4. All right, so that's going to give us negative 5 plus 9 equals 2 times negative 3 plus 4. So that's the square root of 4 equals 2 times, that's the square root of 1. Well, the square root of 4 is 2. And the square root of 1 is 1. And hey, this one checks out. 2 equals 2 is a good solution. Doesn't matter that x equals -1 is our answer. This is a good solution. Give it a happy face. All right, 2 for 2 on this portion of the lesson. All right, let's try another one. And remember to be writing these in your notes, all of the steps. I think I have the other side for you. All right, radicals with odd indexes have a domain of all real numbers. Just a little reminder there. All right, so here we're going to cube both sides. So we have 3 times the cube root of x, all cubed. It's a product. We'll cube not only the cube root of x, but also the 3, equals the cube root of 7x plus 5 cubed. All right, so 3 cubed is 27. Cube root and cube cancel, so this is just x. All right, so you have 27x equals, right, cube and cube root cancel. This would be 7x plus 5. Now we need to solve for x. We're going to subtract 7x from both sides. So we have 20x equals 5. Divide both sides by 20. X is 5 20ths. May as well reduce on this one. So both 5 and 20 are divisible by 5. 5 divided by 5 is 1. 20 divided by 5 is 4. All right, so that's our solution. Let's see if it's a good solution or an extraneous solution. So we have 3 times the cube root of 1/4 equals the cube root of 7 times 1/4 plus 5. Now this one's a little tricky on the checking here. So we have 3 times the cube root of 1/4. Do you know we can't do anything to that to simplify it anymore? Actually, technically, we could take the cube root of the 1. All right, so technically, this would be the cube root, and then you could factor out the 1. It'd be 1 over the cube root of 4, but hardly even worth the effort. So we'll just leave it like that. All right, so let's look at this one. Now we have the cube root of 7/4 plus 5 is how many fourths? That would be 20/4. All right, so this is 3 times the cube root of 1/4 equals the cube root of 27/4. Well, we could simplify the cube root of 27/4, right? Because that's just, so the cube root of 27/4 is equal to the cube root of 27 divided by the cube root of 4. And actually, I am going to rewrite this one a little bit. So I have 3 times the cube root of, so the cube root of 1 is 1. And then we just have it in the denominator there. So I could rewrite that. Look how my writing goes from big to small. Just want to make sure that you get why these are actually going to be, this is actually going to check out. All right, there we go. All right, so I could rewrite that there as, all right, where's my, oh, why do I have an extra 3? Doesn't belong. All right, so I could write that as 3 cube roots of 4, right? 3 divided by the cube root of 4. And that keeps looking like a coefficient when in fact it's just the index of my radical. So 3 divided by, let's make that, there we go, cube root of 4. All right, so now let's continue simplifying this. So 27 is a perfect cube, right? And somehow, again, the 3 is huge. There, it looks better. And the cube root of 27 is 3. And you can't do anything with the cube root of 4, right? Because it's not a perfect cube root and it doesn't have a factor that's a perfect cube root. All right, so that means we could simplify this to 3 divided by the cube root of 4, which is exactly what we have. So sometimes you may have to do some simplifying first. Oops. Oh, what happened to my 4 there? So even though this one had a little bit tricky check there, this one does check out. That's a good solution. We'll give it a happy face. Okay. Right, so now if 0 is the only term besides the radical expressions, you can set the radical expressions equal to one another. Because if that was like a 4 or something, you'd have a much, much, much harder problem to solve. But fortunately, we can just add the cube root of negative x minus 13 to both sides. It'd be on the other side. Right, so if we do that, if we add the cube root of negative x minus 13 to both sides, we'll have the cube root of 1 minus 2x equals the cube root of negative x minus 13. And now we'll cube both sides. Right? So we have the cube root of 1 minus 2x cubed equals the cube root, there we go, of negative x minus 13 cubed. Cube root and cube cancel. We've got 1 minus 2x equals negative x minus 13. Let's get the x's on one side, the constants on the other. All right, so let's add 2x to both sides. That gives us 1 equals x minus 13. All right, negative x and a positive 2x would be x. And then add 13 to both sides. So 14 equals x. Let's check our solution and see if it's good. So we have the cube root of 1 minus 2 times 14 minus the cube root of negative 14 minus 13 equals 0. All right, so this is going to be the cube root of 1 minus 28 minus the cube root. So that's going to be negative 14 minus 13. That's going to be negative 27 equals 0. All right, so that's the cube root of negative 27 minus the cube root of negative 27 equals 0. So that's going to be negative 3 minus a negative 3 equals 0. And of course, minus a negative, that's plus. So we've got negative 3 plus 3, that's going to be 0. And this one checks out. It's a good solution. Let's give it a happy face. Yay! And we solved another one. Right? So not too difficult. You just want to isolate your radicals as much as possible. It's okay if you have a coefficient. You'll just raise that coefficient to the same power as well. It's okay if you've got the difference, sum or difference, right, and it's set equal to 0, then you can just do the opposite on both sides to move that term over. And then you're just raising it to the same power. And let's take a look at this one. I almost thought that was the end of my tape, but no, no, no. So let's check if these solutions are good. And the reason I'm doing this is there is a problem on the whiteboard practice that students have a tendency to miss. I think I put this in your notes, but let's take a look at the first example. If I didn't, you can always write this down. So we have so I'm just going to keep moving. We have the cube root of negative 15 equals the cube root of negative 15. Is that a good solution? They're equal. Negative radicand, odd index. And the answer is yes, that is a good solution. All right, and that's because if you take the cube root or any odd index of a negative, you're going to get a negative, right? So the cube root of negative 8, for instance, is a negative 2 because negative 2 times negative 2 times negative 2 is negative 18. Now, the cube root of negative 15 isn't a pretty number. It's not a perfect cube, but the cube root of negative 15 does equal the cube root of negative 15. So negative numbers under a radical are real numbers if the index is odd. And you can always leave the radicals when you're checking. How about this one? So here we have the fourth root of negative 20 equals the fourth root of negative 20. Well, that's an imaginary number. So now I'm going to move this all down now. Oops, not that way. There we go. What the heck? Where did we go? There we are. I want to get rid of that. I wasn't watching at all. I must have changed the page. So, all right, so that's an imaginary number. Radical equations, we are not using imaginary numbers. So the domain for domain and range, only going to be real numbers, right? It's okay to have imaginary numbers when we're solving quadratics. That's an important solution. They will not exist when we're solving a radical solution, ever. Right? So the negative radicand even index, right? That's going to give us a complex or imaginary solution. There are no imaginary solutions for radicals. All right? So if you have if your answer is the negative, if you have the fourth root of negative 81 equals the fourth root of negative 81, that's no solution because the fourth root of negative 81 is an imaginary number. Right? It's a complex number. All right? So very important. Make sure you don't give me as your answer, right, a complex number. And now, that's the end of my podcast. Now, the reason I went over this, I'll tell you, it occurs somewhere in those problems. Make sure you don't tell me it's a solution if it's not a real number. Right? And so here are your whiteboard practice problems. And I'll, of course, post those. Right? And there's 1, 2, 3, 4, 5, 6. And number 7 is hiding way over on the other. Oh, wait, sorry, that's a Bellward question. Never mind him. Must have put it up some other time. Let's get rid of him. Oops. Maybe not. Whoop. All right, well, just pretend he doesn't exist because I can't get rid of him. All right, so don't worry about him. He won't be posted online anyway. All right, but the rest of it is your whiteboard practice. And bye for now.